Hi, today what we're going to do is talk about building a capacitance substitution box. It's very easy, and we're going to talk about doing it a way that's the cheapest. You can do it by either using dip switches, which is really cheap, which would probably make it cost like $20 or so on all electronics. But the thing is, with dip switches, they're not that reliable, they don't last that long, the hard selected capacitance since they're so tiny, then plus also they're like a chip, and because they're in the package like with the same thing like those through hole chips are. So what we're gonna do is we're gonna use 8 regular switches. This will cost about, maybe this might cost $20 or so on all electronics. Probably cost like 30 for me because I bought some extra stuff with it, but it's gonna cost a lot less. Anyway, here's our specs. The specs here say that we're going to use an 8-bit integer, which is also known as a byte, of capacitance. 0 to 255 microfarads is where you'll be able to select it to. And we're going to use, well, I'm not going to use the cheap dip switches. I'm going to use the regular single pole, single throw switches, Walker switches. Switches with a 1 and 0 on it, so you know if it's set to a 1 or 0. And they're pretty cheap, like 50 cents each. Still not not as cheap as getting like a dip switch. We have all 8 of them or so, or even more, for like $1 or so. Anyway, maximum voltage. This depends. Some of the capacitance you can make have more voltage than others, but we want to make sure that we don't accidentally break a capacitor in it, blow one up, either make it leak or explode because of too much voltage being put into it. So our maximum voltages for the capacitor, since in this one here, the lowest as they would go is like 25 volts DC. We're going to use 25 volts DC. There's some that are 50. There's one that's 100 volt. And there's even one under that's 220 volts, where we're not going to go that high. And it's good for it, and it's usually good to get all of them the same voltages, because then the equivalent series resistance is matched up for the correct thing. Because it's not only is that the voltage rating, it also has something to do with the equivalent series resistance at that certain voltage. And at that voltage, it doesn't really matter because we're going to use it for projects. We're not going to be using it for commercialized stuff where it's like we're going to use to test stuff with the TV. We're not going to use it for anything really commercial like stuff or anything really professional. We're going to do simple projects with this thing, and that's why we're going to use this. Anyway, parts from USA. Every single part of this will come from the United States. You do not have to worry about ordering it from China, Japan, Singapore, anywhere like that, because basically these components are so simple and easy to find that they can find them in all electronics. That's where we're going to get them from. We're going to get them from all electronics. Once you get them from all electronics, you'll be able to build it. Basically, you're going to have to get some solder. You probably could get probably less than $20 for it if you just buy the capacitors in. It just depends on how many bits you want. You can have over 8 bits. You can have up to 32 bits, maybe 64 if you wanted to, but that would be a little high of capacitance. Man, that would be high. And that would be expensive too if you get 64 or 32 capacitors. Then you have to have, well, I calculated with this here, and I got like 11 different capacitors in total of what it was. Doing it this way, doing it the binary coded decimal way. I got 11 capacitors. That's very cheap. That won't cost us hardly anything. 11 capacitors, and it has to be one of each different value. Well, not one of each different value, though, because the 8 bits. Well, what we got some of them in series, some of them in parallel, going around like that to make up the value. Now these capacitors here, they'll be able to handle low voltage stuff. They probably won't be able to handle high voltage stuff. Even if you have capacitors that are weighted and they're differently weighted, if you have the capacitance set for that weight for that one there, they only uses that weighted voltage capacitors instead of the other voltage weighted ones, then you can use that one with it. But the thing is, I like to say the maximum be 25 volts, since mostly all of them are going to be 25 volts. As lowest as you go, the minimum ones that's the lowest one value of voltage it can handle. Anyway, and spend less than $32. You can probably spend less than $32 for it, and that'll get you a good capacitance box that can vary from between 0 to 255 microfarad. You can probably change it if you don't want to do electrolytic capacitors and you don't want to go into microfarad, you want to do nanofarads. You can probably make it 0 to 255 nanofarad, 0 to 255 picofarad, or whatever you want to do it is. Anyway, let's take a look at our circuit here. It's very simple and easy. It looks like a lot of messing with the capacitors and switches, but bear with me. Here we go. Okay, here's the schematic. As you can see here, we got a lot of capacitors and switches here. Over here is the parts list you have. It tells you how many capacitors of each and what the values are. And this terminal block is where your output is. Your output capacitance is. This is where the capacitance you'll get from will come from this. The total capacitance. When these switches flick down and goes down and makes contact, it puts it in parallel with the terminal block. Then it adds that up to it. Now you can see not all of them are in binary. All binary, not the binary number, binary digit number, binary coded form. Like there's 1, and then over here's 2.1 is okay, but look at this one, 2.2 microfarad. It's supposed to be 2 microfarad, but it's going 2.2. And we're going to go over the spreadsheet that I will program that created for me, that web page that created it for me, a server-side script that created it for me, that contains the percentages and what the actual capacitance will be with a certain capacitor. Certain capacitance you select. Tell you the exact capacitance you'll get. And you'll be surprised how good it is. Anyway, then we got there's 4.7 for that one, for the bit 2, and that's supposed to be 4. Then over here, 8 we're doing good because you got 2 of them parallel. We got 3.3 microfarad in parallel with 4.7. If you add those 2 up, you get 8 microfarad, and that will do good. Then in this one, here's our 16. I couldn't find a 16 microfarad from all electronics. I didn't want to go with 10 microfarad because that's like 6 microfarads less. So what I decided to do is take 2 33 microfarads, put them in series. If you have matching capacitors in series, it'll divide them by the number of matching capacitors in series. So if you have 2 of them, it'll be 33 divided by 2. That will give you 16.5 microfarads. So it's like a half microfarad more, but that's not going to make a big difference. Then here, over here is for 32 microfarad, and we got 33 microfarad there. it's only 1 microfarad bigger. We don't really care about that. It's probably going to be tolerance might take care of that for us. Then right here is 64, but instead of 64, we got 66. This is because there ain't no 64 microfarad capacitor. These are using two 33 microfarad capacitors in parallel to make 66 microfarads, or substituting for 64. That's 65, 66, 2 microfarads bigger. Might not make a difference what you try doing, because they're all estimated. Then for the final one, the 108th bit, which is equal to 128, it's 130 microfarad. So it's only 2 microfarads bigger like the other one. You can use dip switches with it, and if you use dip switches, they'll cost a lot less than using regular switches. But the thing is, with them, you probably have to be careful of them, because I think I tried doing this one time with one of them, and it was pretty iffy on how it worked on it. It didn't get best result. So that's why I'm going to use Walker switches. We're going to show you the switches we're going to use and the parts. Okay, let's go take a look at that. Okay, here's the actual price list, and I was pretty surprised of it, just getting everything out of the case. It will come out to be $6.59. That's with all the capacitors and the switches, the 8 switches. The 8 switches add up to be $4. The others are just really in cents. And that's why it makes it so cost less to get it. It makes it so cheap to make. Now let's go to the Excel spreadsheet over here. Get this out of the way. Over here we got selected capacitance, which is the capacitance you choose on the substitution, the capacitor box. Here's the actual capacitance, which will be the actual capacitance you'll get with it. Percentage, which is the percentage of the actual capacitance with your selected capacitance. How much is percentage the actual capacitance of the selected capacitance? Then here's your binary number, which represents the number of switches you need, the switch binary number of what the switches should be switched to get that capacitance. And you can get this from the website, my website. You can go to the link. I have a link in my YouTube this YouTube video down in the description. We can click on this to get this the spreadsheet file in the comma separated values file type, or also known as CSV files. It'll generate the spreadsheet for you. As you can see here, we get to 4.7, which is 4 microfarads. It's 17.5%. 5 microfarads, 14% more. 6 microfarads is 15% more. 7 microfarads is 12% more. And basically it goes on and on with these other numbers here. Some of them are hundreds, some of them 105, 100%, 10%. Not 110%. Those 2.2s are 10%. But these other numbers here go down. Let's show you the average percentage It's all the way down at the bottom, right here. The average percentage is 103.03, or you can say it's 103.04%. And this spreadsheet might actually be a nice thing to have, just in case you're trying to get close to some value and you don't want it to go too much over. And you know, and you can see what the actual value of capacitance it will be if that at certain different switches. And you can say, like, look at this one. This one here. If you go try to get 255, you get 261. But if you type 250 with switching to 250, you get 255.7, which is closer to it. So there you go. They have an easier way of getting that capacitance. This spreadsheet will work. If you don't have Excel or anything on it, you still be able to view it. Then there's be a notepad, and it will not look the easiest to manage. I like it in Excel because it's easy to manage. That's why I didn't do it in an HTML file and stuff like that, because they're not. They have for Android a CSV file viewer. Even if I have Excel, might be able to open up on it. I'm not for sure. Look through these here. A lot of 103% I see. Close to it. And that's why the average would come out to be that. Thing is, it'll vary with tolerance. It may go up, may go down with tolerance. And that's with all of those capacitors that I've chosen. Now let's go over the math about choosing capacitors, just in case you want to use different capacitors than what I selected. Okay, here we are. This is Commodore VIC-20 simulator. We're going to use it to calculate some of the stuff to help you really visualize how to do different kind of combination stuff with capacitors. Since this is what's going to need to be known how to do with it, in case if you want to use different values than what I used. Anyway, in capacitors in parallel, that means having all of them tied together without going in the line, all tied together. The capacitance will be equal to, in series, will add up. So if you have, let's say you want 8 microfarads for the third bit, then that would be let's say you have 4.7 microfarads. Then if we add 3.3 to it, we get 8. Another thing is, now if you want to, now there's other ways of getting capacitance in different ways. It's like series, and what a series does is it decreases the capacitance instead of adding them. It decreases them. How does that? Let's say like you had 233 microfarads capacitors in series. So the equation will look like this: 1 over, in parentheses, 1 divided by, in parentheses, 1 divided by 33 microfarad. And these don't have to be in farads. They could be in microfarad, as long as it's the same unit that you're using. That matters. You can times by 2 or add them. Either which way, times, add, multiplication, division is the same. And you get 16.5 for the fourth bit. These numbers here are binary numbers. As you can know, if you know in computers and programming, binary numbers are ones and zeros that are in a row that add up to, when the ones that have a certain column number, which represents a number you add. If it's a 1 and if it's 0, you don't add it. So let's say we have 65. Okay. The 0th bit of 65 is since 2 to the 0th power, which I can't do on this calculator here. Wish I could. Don't know how. Should be a way. That don't do it. Okay. Anyway, let's stop messing around. Enough of that. For your 0th bit is a 1 in it. Well, 64 plus 1 equals 65, so that means it has to be a 1 now, because it's used to add up to that number. So then we add that to it. What about 2? Well, you can't have 0, 0, and 64. 1 plus 64 is 65, but 0 in there is plus a 1 there for the 2 is 0. So we add a 0 to that bit. Now, for the second bit, the second bit, which is a 4, well, it's not in that combination, so we have that as 0. Then for our bit that has a value of 8, that's a 0. 16, 0. 32, actually that's a 0. 64, 64. Then 128. Well, it's 128 because that's greater than that number. And that gives you 65. That combination. Let's try a trickier one. Let's try 254. Now 254 has all the bits except the last one, a 1. So it'll be a 1 plus 2, since all these bits except for the last one, which is 128, is not used. Or used in it, actually, I mean. Wait, that's 127. What did I do wrong here? 127, yeah, that's right. I'm thinking for a minute. What did I do wrong? I think I know what I did wrong. You think it includes 128 in it. So we did 127 for that one. So that will be 127. I did something. Let's see if we can, hang on. try getting this calculator off in here, see if we can take a look at what I did. Ah, I see what I did. Instead of this bit being 1, it's supposed to be 0, and this bit over here is supposed to be a 1. So if we try that again, if we take 0 for 1, plus 2, plus 4, plus 8, plus 16, plus 32, plus 128. Forgot 64. Go back up here, add 64 to it. That gives us our 254. And basically, you make combinations of binary numbers like that, you can generate up to 255 microfarad. You can go higher than that if you wanted to, but the thing is, why would you want to do that? You could if you could have started at maybe at nanofarads, but nanofarads, microfarads, like 1 microfarad is like lots of nanofarads. Equals to lots of nanofarads. Then you could increase it by that many, how many nanofarads, or even picofarads, but that will give you a lot less though. Anyway, I hope you enjoyed this video. Now let's see, was there anything I'm going to show you? Maybe I'm going to show you what's the difference, how the capacitors are wired in parallel series, since you probably don't know how to do it. I was just telling you how the math goes behind it. So let's go ahead and take a look at how we're going to do this. Capacitors in series will look like this. The capacitor symbol looks like that one I'm drawing right now, this one here. That's a capacitor symbol. And then if we take another one, put it on the bottom of it, sometimes there'll be a different symbol, like this here will be a half circle, the bottom part going from upside down. That's for the polarity that represents the negative terminal of the capacitance. Sometimes they have the plate symbols, sometimes they have other ways. That's in series. Make sure you can. Okay, good. You're seeing this. Okay. So I was wondering if it went off the screen. Make sure. Okay, we're still doing good. Not off the screen. Now for parallel, where to add up on, here's what I mean by parallel. Like that. There's our 2 capacitors. Now we got to connect them. And then you collect one in here too. This one in here is new capacitance here, capacitor there. That's supposed to equal to. And then the new one here. And there you go. That's how you wire capacitors in parallel. And that's about it. So now you know. Better put that down there. That's it in parallel. Well, that's it. That's basically how it works. You can do this with a rotatory switch, but then again, I calculated it up because it goes by 1 plus 2 plus 3 plus 4 plus 5 until you get to 9 capacitors. That will give you 45 capacitors, and this only used like what, 11? A lot less than 45, so you actually save money on it when you do it this way. In fact, I couldn't even make electrolytic capacitor without breaking the budget, without paying an arm or a leg for it. That would use a rotatory switch. Well, I hope you liked this video, and hopefully this helps you make it easy to build a cheap and easy capacitance substitution box. Thanks for watching. If you like it, and also make sure that if you use electrolytic capacitors, these here are the parallel ones. The plus here for this one will be a plus there for that one, and the minus for that one will be the minus for this one. Now for this one here, our plus will be at the top here, not an equal sign. Change that. Delete that, undo it. A plus sign will be here, and your minus will be down here, leaving the plus to this capacitor there, and the minus to that capacitor above it. Kind of like hooking up batteries in series, in parallel. The voltages add up when you put them in series, with the plus and minus are connected to the opposite polarity on each battery, going into the other next battery of the opposite polarity than the one that's coming from the other battery. Hope you learned something for this. I had to make sure you know that, because if you put these capacitors in the wrong way or have them wired backwards, they could leak or explode. And we do not want that to happen. Well, that's it for now. I hope you enjoyed this video. Thanks for watching. If you like it,